ही मतलब अपनी ट्रेनिंग बना ले मुझसे ही छोटा जा वीडियो सारे देख लेना अदरवाइज इवन शेयर विद मी लेटर जे ਤੁਹਾਨੂੰ ਕੋਈ ਲੱਗਦਾ but I am very keenly looking for that application to work.
नहीं मैम वो तो
That was also good. With the headphone test. Sound check. Can I get a to start? So I hope you enjoyed a little bit of hands-on and playing around with the food dyes. Definitely, I always like being hands-on a lot more than being here, dumping a lot of information and not quite sure knowing if it sticks or not in your brains. At least when you're doing something, see that it works. We're now and moving away from microfabrication to think about analytical chemistry and what the whole workflow is to prepare you for tomorrow, an exciting day of HPLC. And then Thursday is our 3D printing manufacturing day, and Friday we'll wrap it all up with some applications in organ on a chip, nanoparticle synthesis and agriculture. So, but we're now going to look how we can miniaturize the analytical workflow and what are the challenges involved. If we can get the slides to move.
I had already done payment for the lens.
There we go. I'd fallen asleep.
For your information, just
So if we think about an analytical workflow, they actually follow very similar steps. So we start off with sampling. We're typically interested in what's happening in a river, in an apple, in a patient, and we can't put the whole patient into the HPLC. So we want to take a small sample of the patient, which could be a little bit of blood, a little bit of tear, a little bit of saliva, and as part of the sampling, it is important that our sample is representative. And unless we look at particles, we probably want to screen the large particles already out, so that we've got only solutes. Because most analytical techniques, we're looking at the compounds our target analytes will be dissolved in the aqueous phase. Then there's sample preparation, which could be solid phase extraction, solid phase micro extraction. It could be isotechophoresis. There's a whole range of different ways that we can do sample preparation. And sample preparation has got one big purpose, and that is to make sure that our assay works as it's supposed to be, so that we don't have any interferences. Nothing in our sample can disturb the assay to the point that the answer that we get out is no longer reliable. So proteins could be an interference, because proteins could be sticking to the surfaces. Some ions could be interferences, particulate matter could be interferences. So it depends on your target analyte what your most likely interferences are and which ones you want to remove during your sample preparation and which ones you want to concentrate. Because unfortunately most of the analytes we're interested in are actually only present in a very small concentration. And our analytical instrumentation is sensitive, but not that sensitive. So we may need to gain a factor 10.
If the Dept is making unnecessary noises when in contact with this microphone, it will be better if you adjust it.
Stay. You just reposition it. Okay, thank you. We had some sound problems. Where were we? So for concentrating our analytes, we may want to gain an order of magnitude or 2 orders of magnitude in order for our analyte to meet the sensitivity range of the analytical technique that we're using. The analytical technique itself could be selective or non-selective. Selective ones are the assays like enzyme-linked immunoassays, PCR, LAMP amplifications for making increasing the amount of DNA present in a sample, whereas a separation could be combined with a universal detector. For example, we can do mass spectrometry with liquid chromatography or fluorescence detection in combination with capillary electrophoresis. But we need to have a selective assay to determine how much of our analyte there is. And that could be selectivity, could be either through the assay or through separation. And ultimately, we need to detect what's going on. So our workflow has very different steps with different purposes. And if we want to put that workflow onto a device or in a box, we need to consider a couple of different aspects. So we looked in here again at the analytical method. We've got the sample preparation and the assay. We had the fluidic operations of the sample, the reagents, and the buffers or the carriers. And then we've got the fluidic control and the communication of the signal to the outside world. And if we're field portable, then we all put that in a box. For the first part of this lecture, I want to focus on how do we actually do that fluidic operation. How do we control the fluids for sample preparation, the assay? How do we make the device that can pump? And can or do we want to integrate the pumps? Sometimes the answer is yes. We want to have an integrated pump because we want to be ultra small and compact. Sometimes the answer is no. We've got such nice little pump systems available that are already field portable. Why wouldn't we just put those in the box with our instrument and we don't need to integrate it on the chip? There is a couple of different parts that we need to consider in the fluid control. We have pumps that could be based on the movement of a stepper motor. For example, pushing a syringe forward. We've got linear reciprocating pumps, we've got rotary pumps, we've got pneumatic pumps that apply a pressure difference to the air body above a liquid and then forcing a liquid through the tubing by that pressure. So they're the pumps. And we've got valves as well, which could be on-off valves that we've seen with the quake valve. It goes all the way down and the channel is closed, or it goes all the way up and the channel is open. So it's a binary valve. There are also proportional valves that can apply an intermediate pressure, so they're a little bit open and a little bit closed, and that is another way of mechanically controlling the fluidic systems. We also have electronic systems that we need to interface with to control our pumps. So depending on the pumps that we have, we may need an analog to digital and digital to analog converters. We need input-output signal conditioning. There may be noises introduced onto our systems that we need to remove again. We may need to get the input of different sensors that monitor what's going on. So pressure sensors, flow sensors, they may all be able to tell us what's happening. We need the electronic systems talk to the mechanical systems, but I need to know what they're doing. And that is where the control systems come in, which is the control algorithms that are optimized through, for example, doing design, simulation and modeling in MATLAB. And then we've got the computer systems that drive it all. And those computer systems could be a laptop computer, it could be a desktop, but more often than not, these are single board computers. Like the Raspberry Pis and the Arduino boards that were shown at the 3D printing lecture, operating the 3D printer. These same little boards that are not very expensive to buy can be used to operate the pump as well. So as a chemist, you pretty much think about a pump as only the mechanical system. You press start and it moves the liquid around. There is actually a whole range of different electronic components that if you miniaturize a pump system down to the microfluidic format, you also need to consider. Yes, maybe it is not that hard to move a barrel up and down in a syringe, and you think that you can build a cheap syringe pump yourself very easily. But by the time you want to have control of your flow rate with the number of steps that your stepper motor sets, there is a whole range of elements that you need to develop with the engineers to have a highly functional pump working. Here we have some of the mechanical ways of moving the fluids. Syringe pumps, you probably know from the laboratory, where we've got a plunger. Where's the slide is even so bad I can't see where the top and the end the plunger are. So this and here's the plunger. There's a stepper motor moving this this block to the backward of the back side of the plunger. And that way the liquid that's sitting here in the barrel is expelled out. Here we've got a peristaltic pump where you can see a controller box and the unit itself, where you can see in this point 3 different rollers that roll over flexible tubing, and every time the tubing is being squashed, the liquid is being pushed forward, and that way we do get positive flow, but we can have a peristaltic flow mechanism. Here we've got the fluogen system, and that is a pneumatic control system, where we've got a little pressure controller that controls the pressure in the headspace of this vial here. We've got a tubing that's sticking all the way to the bottom of the vial. If the pressure in here in the headspace increases, the flow rate of the liquid that's going towards our microfluidic system is increasing. All these systems are available off the shelf. If you've got a credit card with a fair amount of money on there, you can buy a pump. But that doesn't mean the pump will easily fit in your field portable system. So for a lot of these systems, there's also open source instructions available how you can make them yourself. So here we've got a home-built syringe pump where it costs more work to do it, collaboration with an engineering department, but it is more compact and you've got control on all the aspects. Similarly for a peristaltic pump, if you've got a motor that can rotate the rollers around, you can make with a stepper motor your own peristaltic pump. We already saw the mechanics developed to work with the quake valves. That was a pneumatic control system run from a single board computer. Here we've got something very similar, where we've got a series of solenoid valves that can control the air pressure in the lines, and a solenoid valve will be on-off. So it can apply the pressure or remove the pressure following a small electronic signal being sent to the solenoid valve to switch. So the control systems that we have around could be operated in 2 different ways. The first way is that we've got open control. So we've got a signal, a setting that is entered into the controller. The controller sends a signal to the actuator, which is pretty much the pump, the driving mechanism, and the output is a flow rate. And we just trust that flow rate is correct. And sometimes that's fine, sometimes it's not, because sometimes we have a little bit of a blockage inside our microchannels, which means that the back pressure changes. And we all know since the first week that we did this course that if the back pressure, the resistance to flow changes, our flow velocity will change if our input pressure remains the same. So we may get different fluidic behavior if we don't actually check what's going on. And if we implement a closed loop control system, we can actually verify that the input that we told the controller we would like to have is actually achieved. And the control box here is the signal coming from a sensor. So open loop, very easy. We say 5 mils per minute. The pump will deliver it, we hope, but we have no way to check. With a closed loop control system, we have a sensor that checks if the pump is actually putting out what we expected it to do. If it's higher or lower, it adjusts the signal that is going into the controller, and therefore the output is adjusted till it's at the set value. The control system takes a little bit of time to adjust. Here the time is typically in milliseconds, so it's not as bad as it may look like as a flow rate. But you switch the pump on, it takes a little bit to get to the pressure. The sensor figures, oops, I wanted to be at this level, I have overshot, so I need to reduce my signal input and lower my flow rate a little bit. oops, I've overshot that. I need to put a little bit more, and you can see that it's dampening. So after a couple of milliseconds, we have actually achieved the right flow rate, having a closed loop feedback control system. And that way the flow is accurate, and if we've got any disturbances in our fluidic system, we're not negatively impacted by that. We have a lot of different ways of pumping in microfluidics. So we looked at our mixing toolbox before. Our plumbing is either making channels or connecting bits of tubing. Our microfluidic modes of transport. We can move fluids or particles using acoustic fields. We can use capillary forces. We've seen that because we've got such a high surface to volume ratio. We can use the wetting of the channel wall to overcome the air pressure and drag the liquid into the channel. So we can use capillary flow. The microfluidics that we did this morning is a beautiful example where we use capillary forces as a pump. And this morning when we did the quick experiments in the lab, we didn't need any syringe pumps or peristaltic pumps. Once we got the right paper, it just worked as a pump by itself. We'll be talking, I'll be touching on it a little bit today. We haven't seen them yet. They're centrifugal devices, which are pretty much inspired by a CD player, which is a quickly rotating device, and the gravitational force that you create by spinning around can be used to control fluidic behavior inside those microchannels. And I'll give you some rough idea of what's happening. I've deleted and eliminated all the physics behind centrifugal devices. If you're interested, you can study it yourself, but because it's such a niche area, I think enough equations so far. Then there is electrokinetics. We've seen the electroosmotic flow already. So applying a potential difference can be used to generate fluid flow. And then there's of course the pneumatic devices where we apply a pressure difference in the liquid sitting into the air applied to the above the liquid, and that pressure is translated into a flow into the fluidic system. So pneumatic, and then there's also hydrostatic gravity pumps like the syringe pumps. It's a very simple way if you want to do some microfluidic instrumentation, you don't have a pump, is just get a long bit of tubing and put your reservoir containing your liquid a meter above your device. The hydrostatic pressure will most likely be enough to get a significant decent flow through your microfluidic device. With the desire of people to control fluid flow, there's also been the desire to stop it. I'm Dutch. Dutch are known of living below sea level, and that's because we like to stop flow. We like to control what's happening with the water. So what the people before me, I won't claim any contribution to that, have done is create barriers, we call them dikes, and have very good pumps, and we pump all the water out of the dikes to the other side of the dikes. They are reasonably watertight, which means that we can live below sea level. So I grew up near the coast in the Netherlands, and the town is 30 meters below sea level. Schiphol Airport is 45 meters below sea level. But so just by the virtue of having very good pumps in place, we can move the water to the North Sea, and that means that our feet stay dry. So give me a river, and I'll start looking for rocks and see if I can divert the water flows. I just like feeling in control. And people have done that for a very long time. So we have pneumatic tubings where we can apply pressure pulses to control flow. We can use pumps and plungers. They were already, so plungers to pump water up out of wells were already known 250 BC. There have been different fluid logic systems developed to valve and put elements in place at intersections so that flow still could or couldn't work anymore. And by the time microfluidics started being developed, we've had the quake valves being developed where we can close a channel by using the flexibility of a material. We can put them in a circuit. We haven't really touched on that, but we looked at 3 in parallel in line. You can also make a whole grid of these pneumatic valves and have a very complex fluid control network that way. And we can have droplet circuits, like here we can introduce oil phases and have droplets working as little resistors to move liquids one way or another. We already looked at the quake valve in quite some detail yesterday, but I thought it was good to remind us here that in addition to the peristaltic pump, when it's external with the rollers, we can mimic that when we've got a flexible polymer device by inflating the air channels sequentially one after another. If this one goes down, the liquid is pushed that way. If that one is open, there's place to go. If this one is then closing, but that one's still closed, the liquid goes that way. Once this one is closed, this one can open again, allow the next liquid in. And if you do that as kind of moving fingers quick enough, you can start transporting liquids nanoliters a minute. So no huge volumetric rates, but enough to control the volumes that we need for microfluidics. We can only do that in flexible devices. Again, we spoke about soft lithography yesterday, which was the casting in the soft material in PDMS for making these systems. Unfortunately, my magic box that we got approval for to be released to me on Sunday still hasn't arrived. So I'll have my show and tell, I'll share it with you as soon as I get it. We have no idea where it is. So unfortunately, I haven't been able to show you the PDMS yet. We also have a series of active valves, which could be activated pneumatically, electrically, magnetically, thermally. And we've got passive valves, which use the differences in force we need to overcome to transport liquid through a like material to a dislike material. So if we've got a hydrophilic channel and we introduce a hydrophobic patch, we pretty much introduce a break. The liquid quite happily wicks. Liquid is hydrophobic. Stop. And then you need a much higher force for the liquid to then potentially cross that barrier. And once the barrier has been crossed, it is hydrophilic again, so the liquid can run where it wants to go. Here we can see a very simple valve where we've got the inlet. It's a one-way valve, so if the flow goes up, we can see this valve opens and we've got no problem. But the liquid can't go back because it would close this flap, and that means that there's no path. So here you can see a membrane that's been activated by a magnet. So this valve is closed, and that means that the flow can't go up anymore and needs to go around. So we can use just here, no field, the flow will just move this up. When with a magnet we close it, we can't get flow through there anymore. And we've got a small magnetically actuated valve. Now we were talking about the capillary valves that can be used in the centrifugal microfluidic devices. So these are microfluidic networks that are pretty much spinning outwards from the center to the edge of a round device. And during operation it's spun really hard, typically used with me aging, CD players have become decreasingly popular. Therefore there's a lot of very cheap spinners that you can buy and that you can use for your microfluidic experimentation. So the first type of capillary valves is based on having a sudden expansion. Projector is not great, but we can see here just the contours of the microchannel. So we've got a wide microchannel, then it goes through narrowing, and then it goes wide again. The sudden expansion from a narrow area to a wide area, the liquid says, "Ooh, I don't know what's happening here. I can see a lot of air. I stop." So that's a place where we can have a pressure-based stop using a fluidic geometry. Not really strong. If you go at a high spin rate, it's not enough anymore, but it is enough under some circumstances to stop the flow at a low spin speed, and then you ramp up the spin speed and you can fill this channel because the pressure is higher. We just already touched on the hydrophobic valve, and it sounds fancier than it is. It is just having a very small area that got coated with a hydrophobic coating. but the liquid here comes in. Oh, nice, small area, look, a big wall area, I want to go in there. But I don't like the surface anymore, it's hydrophobic. And that's exactly what you see happening here. The liquid doesn't go in unless the pressure pushing is high enough, so you have a high enough spin speed to push this liquid over the hydrophobic valve, and then it can go in the reservoir. The next part here is a siphon valve, where if we're at a high enough speed, the liquid will be pushed this way through the vent and it won't overcome the crest. Whereas if we go slow enough, then this starts pushing the liquid over the crest and it can drain itself into the reservoir. So again, we can use the spin speed in these circumstances to use different geometries. Some are harder to make than others, to control the liquids. The last part that has been really effective in these CD players is to actually use the laser as well that is present in the traditional systems. Because typically a laser was used to scan the CDs and then you got music coming out based on the little dents that were written into the CD surface. You can use this laser as well, it's a red laser, to melt a material. And that way you can remove a valve when you've got a meltable material. Which is called an example of a sacrificial valve. This is just a pressure burst valve. So we've got a sacrificial material sitting there, it stops the flow, but at a certain point the pressure is high enough and this plug that has been immobilized is removed. An alternative for that is using a laser to actually melt. So if this is a little bit of wax, you could hit the wax with a laser. That means that the wax transitions from being a solid to a liquid, just like we did this morning in the lab. We were drawing our things with a solid wax, we put it on the hot plate and it became liquid. Liquids typically have a lot lower flow resistance to solids, so if we melt this wax, we can release the liquid out of one channel to another part of our fluidic structure. The problem with the sacrificial valve is once the plug is gone, the bottle is open and we can't reuse it again. So sacrificial valves are only useful in single-use devices. There we go, so it is still the laser operated one. So our application dictates a lot of what we can do. What is the sample like? What is there for the sample preparation that we need to do? What is the assay? Do we want to do a separation or do we want to do a sensitive assay like an ELISA, or is our target DNA and do we want to do DNA amplification? And how do we want to detect? For the manufacturing, how are we going to make it? We've got a similar set of considerations. To be able to support this assay, what are the materials that we need? What should scalability be like? Do we think that over the coming 3 years of this project, do we need 50 devices but of 5 different designs? Or do we need 1,000 identical devices because we're going to be validating a method that's already established? That determines the scalability of our micropreparation process. Because while we had good fun in the lab this morning, I saw that we had a big queue up to the hot plate. This morning we could make probably 20 devices. We couldn't have made a lot more because we all needed to hand draw them and then put them on the hot plate and take them off again. There was a lot of manual interaction, which means that the throughput of paper fluidics is not really high when you're drawing with a crayon. If we would be using the wax printer that doesn't exist anymore, we could actually make our devices by an A4 sheet at the same time. We may be able to accelerate our max welding. Instead of using a small hot plate, using an oven and have 3 or 6 sheets in the oven at the same time. So if you think about the process, some of the paper fluidics could be scalable, but what we did this morning with hand drawing and a small hot plate, it certainly wasn't very good for scalability. The other thing we need to consider is how far do we want to go towards integration. Technology-wise, the more integrated the better. And I love functional integration, hence we're talking about it now. But sometimes actually we should be happy with just being modular. sometimes it's actually not bad to have a sample preparation part to your chip and a separation part of your chip. Put them together like Lego blocks. If one is broken and the other one is not, you can just replace one module. Has its advantages as well. That's not a... Hold on. So the chip design can start off with a simple hand drawing in a lab book. Then graphical packages like CAD software or SolidWorks are good ways of making the designs. The design that you have makes your geometry, so it shows you where your channels are and where they're meeting or not. Your depth is typically determined by your microfabrication approach. This morning our depth was defined by the thickness of the paper. If you etch, your depth is defined by how long you keep for glass etching your device in the liquid HF. 2D drawing is relatively easy. The design rules work based on the hydrodynamic resistances, which function like electronic resistances. So if you want to have two liquids ending up at the same point at the same time, we need to make sure they have the same resistance, which means that ideally they have the same length and width. If one is wider, it needs to be longer. So we can play around with them, we can calculate, and there's even some smart microfluidic design packages that do the calculations of the flow resistance for you. Serpentines, we've already looked them at calculating what the length were or what the number of turns were that we were going to need to make a micro mixer. Serpentines are really good to put a really long channel on a very small surface area. If we have a large chamber to do an immunoassay, we can have a flow distributor that ensures that our fluid, our chamber is filled equally from the left to the right. And it is important to always be mindful that at some point we need to interface with the big scary world. And any fitting with the big scary world is large compared to our chip. So make sure you leave enough space to have your reservoir, because either you want to glue on a pipette tip or you want to glue on a fitting. That fitting needs to be held by your fingers. And therefore it is 5 to 10 millimeters in size. If you want to watch what's happening in your channels, make sure the channels where things are happening that is interesting are not close to those connectors, because your UV glues you use to attach your reservoirs to your chip are often fluorescent. So if you want to look at an analytical step in your processing and all you can see is your glue, it's a very difficult experiment to do. So knowing where your inlets and your outlets are is an important part of thinking through your plumbing in your later use. 3D printing, we'll be talking about that going into the additional dimension on Thursday, is hard because at school we draw in 2 dimensions. In everyday life, if we talk in the lab, talk with colleagues about some fluidic structures, we go 2-dimensional. Most 3D printed devices we can see in literature are actually 2-dimensional drawings, because our brains, maybe the next generation coming through high school is good at 3D, but most of our brains really struggle to think about 3-dimensional fluidic networks. Layering can save space, so you can have different fluid layers on top of each other, but it makes imaging more complex. So what is more important, what's not? So I want to quickly, and I see that time is running faster than I thought it would be. There are some examples in forensic science where we've got pre-processing. So if there has been a rape, there's a crime victim, we have sample preparation to do the serology at the crime scene. These samples are being packed, as you can see on all the television series. At least I like crime series. Then there is in the lab, there's extraction, quantification of the DNA, amplification to know what the profile is, separation of the amplicons by capillary or by gel electrophoresis, interpretation of the results that are then sent to a person. How much of this workflow can be, so ideally microfluidics can be designed with the end user in mind, but the design we need to work across disciplines. Here we have kind of 2 end users. We've got the person that's in the field that needs to take the sample, package it up and operate the instrumentation. And we've got the decision maker, which was the person sitting there that needs to check the results. So we've got two end users, the operator and the person checking the data. They may not be the same, but both of them need to be happy with the reliability and the speed of the method. We have a lot of advantage of miniaturization. We've got our increased surface area to volume ratios. I decided to leave a lot of the text on here. So we've got fast analysis time, increased sensitivity, small footprint, low cost if we can scale. We can increase our efficiency. The driver originally for miniaturization was to increase efficiency, and we can therefore enhance the assay sensitivity as well, using the microfluidic processes. The big advantage in forensic science is that we can directly analyze samples at the crime scene rather than have to transport to a laboratory. But miniaturizing instruments is also advantageous if you've got a laboratory that's relatively small and you want to run a whole range of different methods. Theoretically, small volume of reagents should be a money saver, but only once you've paid for the cost of development of the miniaturization. So for some assays we're there, but for most of them we're still paying the development cost. The struggles in microfluidics in getting this complex analytical workflow actually integrated are connects between academics and professionals in the target markets. We rarely develop something with the end user in mind. We just have a really cool assay that's brilliant in our lab, we think as academics, and we don't think about manufacturing challenges, we don't think about the salesman, we don't think about the end users. There are very, very few, and I know none, fully integrated systems. So there's always some manual step or some big element that's still there. Miniaturization of the full analytical workflow, even though Andreas Mans came up with the idea in 1990, it is still hard to realize. There's a lot of challenges on the way to get to this ideal box that you put in your backpack and you can do all tests that you want everywhere on the world. There's also a lack of standardization, which is a little bit of a conundrum because we like to be creative, we like to develop new processes, and therefore we don't want standards. But if we want to integrate it, the whole process, then actually having standards for how different parts interface would be really good. So there's discussion going on, should we move towards more standardization, like a lot of industries in microfluidics, or are we too attached to our little playgrounds in the lab? For the integration of the process, aim for the highest level of integration that you can get to. Commit to a mode of liquid transport that is compatible with all processes. Select a material that is either versatile or affordable. Incorporate modular elements where you can, because they're easier to swap out. And interface with a support instrument that can easily be serviced. World-to-chip interfacing is a big challenge that I don't think I'll have. Let's see how many slides I've got left. So let's just go quickly. So if you've swapped aside for some biological materials, that's done with a cotton swap. And that's typically cut off with a pair of scissors. This is very large compared to a nucleic acid device, and it releases dust. So washing out other materials to get to the biological samples also ends up with really, really large volumes. So interfacing the place where we're sampling from and the place where we're doing sampling is, we're talking 4, 5, 6 order of magnitude in volume, which is a challenge to do. How ideally you deal with a large sample volume is use enrichment techniques where you can process through a large volume and concentrate your analytes in a really small place. Employ modular systems, not in series, but in parallel, because that way you can process larger volumes at a time. Practically, there are still big challenges to interface with the big world. There's little filters that you can use to pump tiny amounts of liquids into the chips, but the overcoming 4 orders of magnitude in sample volume continues to be a challenge. Sample to answer systems are available, And nucleic acid preparation is one of the areas where they have become most available. Let's see what I put in there. Yeah. So we'll be talking through the development. So nucleic acid analysis is very important in forensics and had a lot of money going around in the US. So I'll talk you through the way that a miniaturized total analysis system for genetic analysis has been developed in the US to see what the drivers were of the decision making. In this case, we want to measure DNA, and DNA needs to be amplified. So PCR has different aspects to it. We have some people with biology, it's an enzymatic conversion. So we need an enzyme, we need to know when the enzyme is operational in order to convert the amplification. There are chemical aspects, we need primers for our PCR to work, and certain salt concentrations, because if we haven't optimized the magnesium, our PCR is not working. We have physical constraints to our PCR. We need thermocycling, which we can achieve in different areas. In a flow system, where we flow through hot and cold regions, we can heat up and cool down the whole chamber, and we can also do PCR in droplets. The reagents, if we don't want to do cold storage, we can actually lyophilize them onto the chip so we can move them around. Very long time ago, we had a complete DNA assay ready to commercialization and thought it was going to be 2 years to the market to do all the sample handling with nucleic acid analysis. So we ended up with having domains for DNA extraction here in yellow, followed by PCR, amplification of the DNA in red, and the gel separation happening in blue. So sample would be introduced from a swab into the sample here. There would be a silica column to extract the DNA. There would be an elution step to elute the DNA into the amplification region. That would be thermocycled, all the reagents were dried in. Then the amplicons would be transported electrokinetically to the intersection here using the cross injection that Professor Bagat talked about. A small sample zone was introduced here in the separation channel, and then our DNA peaks would be detected here with laser-induced fluorescence detector. Really cool, worked, but it was an injection molded device. There were no integrated electrodes, and it ended up being too expensive. So the group got back to the thinking board, and 10 years later, there was an alternative being developed of exactly the same device, but then made from some paper backing, some gold leaves to provide electrodes, some pressure-sensitive adhesive, and some overhead transparencies. Really, really cheap materials, because there was no way they could make a business case based on an injection molded device for the scale they were working at. So they had to go back to the drawing board and use a centrifugal device, because CD players are easy to get. Version for the liquid transport had little pneumatic systems and solenoid valves. In commercialization, they were not sufficiently reliable. So they broke, there were leaks, 10 years of engineering, and they ended up with a much cheaper device made on an overhead transparency. And that has then been commercialized. So it needs to be really, really cheap if you want to sell a fluidic device, because otherwise it's not going to get the market. This is the part where they changed the lysis to centrifugal device, where they have, here are the enzymes waiting for the amplification. The sample goes in here. There's the sample in pink. Centrifuge goes on. The sample is loaded into an area that already has got some magnetic beads. The negative charge in presence of high salt binds the DNA. If we open this valve with the laser, we can get rid of our waste. The DNA can remain stuck to the beads. We can have some washing reagents flushed over. That's happening here. The wash step came from there. And then we can amplify this chamber after the insertion of the amplification reagents, and we can do the PCR there. No need for valves, no need for manual handling, all happening on an overhead transparency, printed with a normal office laser printer. So the lessons learned from, and then the review that is there is actually written by the person that went through all this development, James Landers. And it goes through the journey and all the mistakes that they've made on the way. Important lessons are, be modest with scope. Don't promise that you will be able to identify any perpetrator from a tiny amount of sperm sample that wasn't stored really well. If it's a forensic test, you want to quantify DNA. Understand what the conventional workflow looks like, because for any evidence to hold up in court, you need to be as close to the standard methods as possible. Miniaturization included the workflow in having extraction, PCR for amplification, and then the gel separation. Multi-step flow makes life hard. Because a slightly different approach was formed, the answers that came out, the change in format not separating in a capillary build on a chip, means that the large databases that are existing in the US of people where they've had their DNA sample taken before can't be cross-referenced. So there was a data incompatibility. There was not enough thought about the end user when they designed the whole workflow, because there was no compatibility with the format of the data that was already present in the databases. So, not to end up on a depressed note, but if you want to embark on anything in microfluidics, be aware that doing isn't hard. We need to understand the physics, where we've got change surface to volume ratio and changed mixing. We need to have control on the process of what's happening. While we can automate our liquid handling, all steps will add complexity. So think through your chip layout and keep it as simple as you can. Minimize your number of control elements that you have and make them easy to operate. And functional complexity, think if there is a way that you can go modular, because you can optimize each of your individual components and then stick them together one by one. Connecting any types of functional elements is challenging, and it also complicates manufacturing. So it's always a little bit of a compromise. I love functional integration. My whole team is focusing on it. But sometimes you just need to have common sense, and assembly of a couple of modular components could be common sense as well. So be mindful of what's happening. There are horses for courses. Sometimes it's a nice engineering project. Sometimes it just needs to work, and maybe it is a suitcase instead of something that's handheld. But it is, if it does the job, it's good enough. So with that reality check, I think I need to get into my car to get to Amritsar, and I hope that you guys will have a fun time tomorrow learning all about HPLC. And I'll see you again on Thursday talking 3D printing. Thank you.
I need to drop you.
Okay.
Malik